Hi, thank you for joining me on this screencast. This screencast or tutorial is about electron configurations, and this will be the first video of a series introducing you to what electron configurations are and how to draw them. In this video, we're going to focus on writing electron configurations using orbital diagrams. Now, before we get into this, I wanted to take just a moment to review basic atomic structure. Okay, remember, an atom is formed from three subatomic particles: the protons, neutrons, and electrons. Okay, together, the protons and neutrons make up the nucleus, which is found towards the middle of the atom, and around the nucleus are the electron shells, in which electrons are thought to move around the nucleus. Okay, remember, protons have a positive charge, electrons have a negative charge, and neutrons are neutral. Most of the mass of an atom comes from the nucleus, whereas most of the volume or the size of the atom comes from the electron shells. Before I show you how to do orbital diagrams, I wanted to show you what an electron configuration looks like. So this is a table of elements 1 through 15. This column to the right shows their electron configuration. Now, I know that these electron configurations may look a little bit weird or bizarre to you at first glance, but don't let that overwhelm you, because the electron configurations are actually quite easy to figure out. Okay, before we move on, I wanted to introduce to you some vocab, key vocab. Okay, the first word or term is energy level, sometimes also called energy shell. Okay, so you can think of an energy shell or an energy level as a layer where electrons can be found around the nucleus. And here are some pictures kind of illustrating the various energy layers of the hydrogen atom. Okay, notice the nucleus is in the middle, and then it says n equals 1, n equals 2, n equals 3, and so on. Okay, the first energy level is the energy level closest to the nucleus. The second energy level is the next farthest energy level out. The third, the next farthest out after the second, and so on. Okay, it may be helpful to think of the energy shells almost like rungs on a ladder. Now, in this case, the rungs on the ladder would not be evenly spaced. What happens is the further we get away from the nucleus, the closer the rungs, or the closer the energy shells get. Now, just like a ladder, the most stable part of the ladder is the bottom rung. Okay, the most stable energy level, which is what we say energy level with the lowest energy, is the energy level closest to the nucleus. The second vocab word I wanted to introduce is the word sublevel, sometimes also known as subshell. Okay, so all energy levels can be broken down into sublevels. The sublevels are called S, P, D, or F. Okay, now sublevels are technically groupings of electron orbitals. And that leads us to the next vocab word, the word orbital. Okay, orbitals are the spaces where electrons are likely to be found around a nucleus. The orbitals have somewhat bizarre shapes, and these shapes are predicted by quantum mechanics. Okay, an S sublevel consists of one orbital. It's this spherical shape, and that one orbital holds a maximum of 2 electrons, right? Each orbital holds up to 2 electrons. So an S sublevel holds 2 electrons. A P sublevel consists of 3 orbitals, 1, 2, 3. If each orbital holds up to 2 electrons, that means a P sublevel holds up to 6 electrons. A D sublevel consists of 5 orbitals, 1, 2, 3, 4, 5, and a D sublevel holds up to 10 electrons. The F sublevel consists of 7 orbitals, and if each one holds 2 electrons, that means an F sublevel can hold up to 14 electrons. Here we are looking at our very first orbital diagram. Okay, an orbital diagram is a visual depiction of all of the electrons in an atom. In an orbital diagram, there's numbers letters and dashes. The numbers, like 1, 2, 3, 4, 5, and so on, indicates the energy level. The letters, S, P, D, and also F, F's not shown in this orbital diagram. The letters indicate the type of sublevel. And then a dash represents an orbital, one orbital. Okay, so each dash holds up to 2 electrons. When filling out an orbital diagram, there are some rules that must be followed. The first rule is that each electron is represented by an arrow. The second rule is known as the Aufbau principle, which tells us that electrons always fill the lowest energy orbitals that are available first. The next rule is Hund's rule, and it applies when we have a sublevel, such as a p sublevel or a d sublevel, with multiple orbitals and multiple electrons. Hund's rule tells us that electrons will always tend to spread out and occupy empty orbitals before they pair up. The last rule is known as the Pauli exclusion principle, which tells us that when there are two electrons in one orbital, the electrons will spin in opposite directions, which is represented by an up arrow and a down arrow. The reason they do this is electrons are negatively charged, and two negative charges in the same space are going to have repulsion effects. And so the electrons will tend to spin in opposite directions, which minimizes those repulsive effects. Okay, so here's an example of an orbital diagram being filled out. Here's the beginning. So then we go to the 2s and then the 2p. Okay, there's a series of questions that go along with this. So again, here's the beginning. Starting from the bottom and working our way up the page. Okay, again, here's the beginning. Starting at the bottom, working our way up the page. Okay, here's a series of questions. Based on information on the previous slide, I want you to pause this video and see if you can answer these 5 questions based on this orbital diagram example for neon that's being filled out over and over again. Okay, now that you've had a chance to answer these questions, let's go through them real fast. Okay, first of all, note that neon has 10 electrons, and therefore there's 10 arrows added to the diagram because each electron is represented by 1 arrow. Number 2, why is the first electron added to the 1s orbital? This is due to the Aufbau principle, which states that the lowest energy orbitals always fill first. Number 3, why is the second electron added to the 1s orbital and not the 2s orbital? This also is based on the Aufbau principle, which says that electrons will always occupy the lowest energy positions first. Even though the second electron would have to be paired up in the 1s sublevel, there still is a position in the 1s sublevel which is lower in energy than the 2s sublevel. Okay, number 4, why is the second electron in the 1s orbital written as a down arrow? This is due to the Pauli exclusion principle. Remember, whenever there are 2 electrons occupying the same orbital, they will spin in opposite directions, which is represented as 1 up arrow and 1 down arrow. Okay, number 5, why is the 6th electron written in the second 2p orbital rather than the first 2p orbital? Okay, so this is 1, 2, 3, 4, 5, 6. The question is referring to the electron right here. And that is connected to Hund's rule, which says that when there are multiple orbitals and multiple electrons, electrons will tend to spread out, occupying their own orbital before pairing up. Okay, let's take a look at our first example. So here we're going to looking at the element neon. And we'll go ahead and fill out the orbital diagram or orbital notation, as well as look at a Bohr model, a Lewis diagram for neon, and then finally write the electron configuration for this element. Okay, if we go and look at the periodic table, neon is located right here. It is element 10. which means it has 10 protons. And as a neutral element, neon would also have 10 electrons. Okay, so we'll make a note, there's 10 electrons. Now what that means is in my orbital diagram, I need to have a total of 10 arrows. Okay, starting from the bottom up. Here we go. Off-bar rule, start at the 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I've added the 10 electrons to the orbital diagram. Now the Bohr model. The Bohr model is a simplified way of representing the shells, or the energy levels, that are occupied by electrons. Okay, so in this case, we have two energy levels, the 1 and the 2, that are occupied by electrons. And so this means that we need to have two shells in our Bohr model. In the first energy level, 1s, there's 2 electrons. Now in the Bohr model, you represent electrons as dots. And so in this first shell, I need to have a total of 2 dots, representing the fact that there's 2 electrons there. In the second level, okay, we have electrons in the 2s and the 2p, but those are both part of the second energy level, right? So there's a total of 8 electrons in the second energy level, 2 from the 2s and 6 from the 2p. So we'll go ahead and write 8 dots on this second shell here. Okay, and now we can actually state what I call the shell configuration. Okay, in the first energy level, there are 2 electrons, and in the second energy level, there are 8 electrons, represented as 2-8. 2 electrons in the first energy level, 8 electrons in the second. Okay, for valence electrons, the valence electrons are electrons found on the outermost layer of an atom. And valence electrons are in the outermost S and P sublevels. So the outermost S and P is the 2s and 2p, and there's a total of 8 electrons in the outermost S and P. Okay, so there's 8 valence electrons. To do the Lewis diagram, you draw the symbol of the element, and then the number of dots, same number of dots as there are valence electrons. So in this case, there's 8 valence electrons. I would have 8 dots around the symbol Ne. Okay, let's now go and draw the full electron configuration for neon. Okay, and we do this by basically reading off the orbital diagram, starting with the 1s. And any of these orbitals that are occupied with electrons are going to show up in our electron configuration. Okay, so it looks like the 1s has electrons in it, 1s, and there are 2 electrons in there. So we're going to say 1s2. Moving up, it looks like the 2s orbital is filled. So we have 2s, and there's 2 electrons in there. Okay, next, it looks like the 2p has electrons in it, 2p, and there are a total of 6 electrons there, so 2p6. Okay, noble gas configuration. Well, if we go back to the periodic table, remember the noble gases are these elements in the far right column. Neon is in that column, so neon's actually a noble gas. So in this case, the noble gas configuration doesn't do us a whole lot of good, but you'll see how it's helpful on the next example. So because neon is a noble gas, we could write its noble gas configuration as just Ne in brackets. And what that is it's basically shorthand for all of this stuff up here. 1s2, 2s2, 2p6. Okay, brackets Ne symbolizes the full electron configuration for neon. Okay, let's go and look at the next example. Sulfur. Okay, so if we go to the periodic table, sulfur is element S. right here. And sulfur is element 16. Okay, so there's 16 protons in sulfur, and as a neutral atom, there will also be 16 electrons. That means I need to have 16 arrows in this orbital diagram. And as I fill this out with the 16 arrows, I need to make sure I follow the Aufbau principle, Hund's rule, and the Pauli exclusion principle. Okay, starting from the bottom and working my way up. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See, I've placed my 16 arrows or electrons following our 3 rules. Okay, now to do the Bohr model. So looking here at the orbital diagram, I notice that I have electrons in the first, the second, and the third energy levels. Now what that means is my Bohr model needs to have 3 shells. So there's 1, 2, and 3. Okay, now in the first energy level, 1, there's 2 electrons. And I'll draw that as 2 green dots. 2 dots representing 2 electrons. In the second level, we have 2s and 2p. There's a total of 8 electrons there. 2 from the 2s and 6 from the 2p gives us 8. So in the second energy level, I will draw in 8 dots representing the 8 electrons that are there. Okay, and then in the third energy level, we have the 3s and the 3p. And in the third level, there's a total of 1, 2 from the 2s, and 4 from the 3p. So that's a total of 6 electrons on the third level. Okay, now if I were to draw or write the shell configuration, in the very first energy level, there are 2 electrons. In the second energy level, there's a total of 8, 2-8. And then in the third energy level, there's a total of 6, so 2-8-6. Okay, number of valence electrons. These are the electrons again on the outermost s and p sublevels. So 3s and 3p are our outermost s's and p's, and there are a total of 6 electrons there. Symbol for sulfur is S, and if there's 6 valence electrons, I would draw 6 dots around the sulfur. All right, now for the full electron configuration. So I'm going to read off of the orbital diagram starting from the 1s. Any sublevel with electrons in it shows up here. So we have 1s, and there are 2 electrons in the 1s. Okay, next 2s, and there are 2 electrons there. Next 2p, and there are 6 electrons there. Next 3s, and there are 2 electrons there. Next 3p, and there are 4 electrons there. Okay, this is the full electron configuration for sulfur. Now this is where the noble gas configuration is going to come in handy. Okay, now remember last example, we found the electron configuration for neon. Okay, and the electron configuration for neon was 1s2, 2s2, 2p6. So instead of writing the 1s2, 2s2, 2p6 over again, you could just represent all of that stuff as neon brackets, right? So that represents 1s2, 2s2, 2p6. And then after the brackets, we would write what's left. In this case, 3s2, 3p4. Okay, and that would be the noble gas configuration for sulfur. Okay, there's one more example. Argon. Oh, actually, my bad. There's two more examples. Argon. So argon is element number 18, found right here. It means it has 18 protons, and as a neutral atom, it's also going to have 18 electrons. So that means in my orbital diagram, I need to have 18 arrows following the three rules: Aufbau, Hans, and Pauli exclusion. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, Bohr model. I notice that there's electrons in 3 energy levels. So I need to draw 3 shells. 1, 2, 3. Okay, in the first energy level, there's 2 electrons. In the second energy level, the S and P together, 2 and 6, gives 8 electrons in the second energy level. And then in the third energy level, 3s is 2, 3p is 6, so again 8 in the third energy level. And then if I were to write the shell configuration, it would be in the first level, there's 2, second level, there's 8, and third level, there's 8, 2-8-8. Number of valence electrons in the outermost S and P. So 3s and 3p are my outermost ones. There's 2 in the 3s and 6 in the 3p. 2 and 6 gives me 8 valence electrons. Lewis diagram for argon. Argon is symbol Ar, and because there's 8 valence electrons, I would draw 8 dots around the symbol Ar. Okay, that's the Lewis diagram. Now full electron configuration. Starting from the 1s, anything that's any sublevel that's occupied with electrons, we'll read from there. So 1s, and 1s has 2. 2s has 2. 2p has 6. 3s has 2. And the 3p has 6. Now if we go back to the periodic table, again, argon is a noble gas. So the noble gas configuration for argon is going to be brackets, and then the symbol for argon. And again, what that represents is all of this stuff up here. Shorthand for all of this. Now let's go and do the last example. Okay, arsenic. Arsenic from the periodic table is element As, right here. Element 33, so it has 33 protons. A neutral atom would have 33 electrons, which means I have 33 arrows that I need to place in this diagram, okay, following the 3 rules: Hans, Aufbau, and Pauli exclusion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Okay, so now for the Bohr model. Now when I'm looking at this, I'm noticing that arsenic has electrons in the 1, 2, 3, and 4th shells. or fourth energy levels. And so that means my Bohr model needs to have 4 shells. There's 1, 2, 3, and 4. Okay, in the first energy level, in the 1, there's 2. So we'll put my 2 electrons there. In the second energy level, 2s and 2p, there's a total of 6. There's a total of 8. Sorry, 6 in the 2p and 2 in the 2s. 2 and 6 is 8. Okay, in the third energy level, now be careful here because we have 3s, 3p, and 3d. So in the third level, we have to add up all of these. So there's 10 in the 3d, there's 6 in the 3p, which is 16, plus 2 more from the 3s, which is 18. I'm going to put 18 electrons in the third level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, and then in the fourth energy level, again, careful, we gotta look for all the places with 4s. We have 4s and 4p. It looks like there's 2 and 3 for a total of 5. 1, 2, 3, 4, 5. Okay, now for the shell configuration, well, on the first level there's 2. So 2 dash. On the second level there was 8. On the third level there was 18. And on the fourth level there was 5. Okay, number of valence electrons. So outermost S and P's. So 4 is our outermost energy level. 4s and 4p, those are our outermost s's and p's. There's a total of 5 electrons there. Okay, symbol for arsenic is As, and it has 5 valence electrons. So 5 dots around it. Now for the full electron configuration. We have electrons in the 1s, and there's 2, 2s, 2, 2p6. Okay. We have electrons in the 3s, and there's 2 of them. We have electrons in the 3p, and there's 6 of them. Electrons in 4s, and there's 2 of them. We have electrons in the 3d, and there's 10. And then we have electrons in the 4p, and there are 3 of them. Okay, now this, you can see the full electron configuration got pretty long, honestly. When we did argon last time, we saw that argon's configuration was all of this stuff right here. So the noble gas configuration is a way to write this shorter. And instead of writing all of that stuff, I could just put argon in parentheses. Not in parentheses, in brackets. And then after the brackets, whatever's left. So in this case, 4s2, 3d10, and 4p3. Okay, so now I'd like you to stop the video and work out one of these, fill out one of these tables for A for silicon. Then after you do it for silicon, do it for cobalt. And I will show answers following. Okay, now that you've had an opportunity to work these out, hopefully, here's the answer for silicon, or silicone, however you want to say it. Go ahead and pause the video to check your answer. And here is the answer for cobalt. Again, go ahead and pause the video as needed so you can check your work. That's all for this tutorial on writing electron configurations with orbital diagrams. Thanks for listening. I hope this was helpful, and if you have any questions, please leave them in the comments.